Good afternoon, everyone. I'm David Hahn. I'm the Craig M. Berge Dean of the College of Engineering. I'd like to welcome each of you to our first webinar of the Spring 2023 Alumni Faculty Lecture Series. Our goal remains the same, to share discussions on important topics and have a conversation with our alumni and friends, including many of you who generously support this college and have truly helped to make this happen. I often talk about the most significant challenges that face society, including food and water, energy, healthcare, and security, which includes economic security. And today our conversation will dive into a subject that is critical not just to the University of Arizona or to the state of Arizona's economy, but one that has global implications, and that is the semiconductor industry. It's a very exciting time as the United States is galvanized behind a goal of more domestic production of chips. And to help this, the CHIPS Act is designed to bolster U.S. leadership in semiconductors, to promote U.S. innovation in wireless supply chains, and to advance U.S. global leadership in the technologies looking forward of the future. Arizona plays perhaps the most important role of any state, with up to $60 billion being invested by Intel and TSMC alone right now. The Arizona Commerce Authority has $100 million to invest, including in university infrastructure to support research and workforce development. So as I said, it's really an exciting time. To discuss these issues in depth, I'm delighted to be joined by our faculty member, Sammy and by Chris RUMER from Intel Corporation here in Arizona. So let me formally introduce Chris and Sammy, and then we'll get into the conversation. So again, thanks for joining us today. So Chris RUMER is Vice President of Technology Development at Intel Corporation. Chris has over 26 years of experience with Intel. He has also served as Director of Assembly Engineering since 2011. Chris earned his BS in Mechanical Engineering from the University of Michigan and a Master's in Material Science from Columbia University. While not a Wildcat Engineering alumnus, I am very proud to note that Chris does serve on our college's Dean's Advisory Board, helping to guide us on today's important topic, semiconductors, as well as other things around workforce and engineering excellence in research and education. He also has an MBA from that university to the north. Chris is a true thought leader, and we're glad to welcome you today with us, Chris. Welcome.
Thank you, Dean.
Also with us today is Dr. Sammy Tin. Sammy currently serves as Department Chair for Material Science Engineering, where he holds the Patrick R. Taylor Endowed Chair in Material Science and Engineering. Before joining the University of Arizona, he worked for 15 years at the Illinois Institute of Technology, most recently as the Charles and Lee Finkl Chair of Materials Engineering and the Director of the Thermal Processing Technology Center. Sammy received his PhD in Material Science and Engineering from the University of Michigan and has been a wonderful addition to this college's leadership team. So welcome, Chris and Sammy. So before we dive into our chat and our Q&A, Chris and Sammy will present a few slides to help frame this discussion. We'll start with you, Chris, and then move to Sammy afterwards. So Chris, feel free to share your slides and give us some additional insight.
Okay, thank you, Dean Hahn. So I'm going to talk a little bit about Intel's presence and investment in Arizona. Okay, can you see the slide okay?
Perfect.
All right, great. So Intel has invested in Arizona since 1979. We have, pretty large presence in the state. Direct employees, we have 12,000. We've contributed about $4.9 billion in labor. We indirectly support about 55,000 jobs in the Valley and throughout the state. We contribute about $8.6 billion to the GDP. We have so far invested about $32 billion in capital investments, and we recently announced future investments of $20 billion in the state. So a very, very large foothold and presence in Arizona. In September 2021, we broke ground on 2 new fabs in the Ocotillo campus, really helping to grow our manufacturing capacity in the state. We're creating about 3,000 high-tech jobs working in these 2 fabs. We've also got about 3,000 construction jobs and an additional 15,000 indirect jobs, supporting that facility. The campus I work on is a little further to the north in Chandler. We have about a 200,000 square foot advanced packaging R&D center. And we work on advanced packaging solutions for all of Intel's products. So we can combine the silicon die with an organic substrate and then add other packaging solutions like heat spreaders to them in order to finish the final product. In advanced packaging, the focus is on protecting, connecting the chips together, and then re-architecting the product, combining many things together. And what we've seen in recent years is we've moved from single die and multi-chip packages to more of a chiplet-based solution. And all of this technology is developed in Chandler, Arizona. You can see some examples of our advanced packaging solutions. We have the embedded multi-die interconnect. This technology we introduced several years ago on our FPGAs, and then more recently on our server products. Sapphire Rapids uses this packaging technology. We actually connect 4 individual CPUs together in a single package in order to increase the number of cores available on that server product. We've also delivered the Phobos technology. We've done a low volume product called Lakefield a few years ago. And then later this year, this will be ramping into high volume manufacturing for our Meteor Lake client solutions. This is for both laptop and desktop computers. We're working on future packaging technologies too, called Phobos Omni. This is another way of connecting chips together using a smaller bridge as part of the base die underneath individual chiplets. And then we've also got a technology called Phobos Direct, and this is utilizing hybrid bonding to connect chiplets to a silicon wafer. And so you can see an example here. Our packages now include multiple different small chiplets using different silicon nodes, all connected together at very, very fine pitch to complete the finished product. And as I mentioned, all of this technology is developed in Chandler, Arizona on this campus. As we look at the future, we've set some very aggressive goals as part of RISE 2030. RISE stands for Responsible, Inclusive, Sustainable, Enabling. And if you look at the 4 different focus areas, under responsible, we want to revolutionize how technology will improve health and safety, not only of our employees, but of people around the world. We also want to make sure that we're inclusive. We make technology fully inclusive and expand digital readiness to everyone. And this also includes our hiring practices and making sure that we have an inclusive and diverse workforce. Another focus area is sustainable, so achieving carbon neutral computing to address climate change. And this is, not only as part of our manufacturing solutions within the company, but also trying to reduce our overall environmental impact of the products, as they're used by our customers. And then finally, enabling is accelerate the ways we enable progress through our technology and the expertise and passions of our employees. And a couple examples of these RISE 2030 goals. There's been a lot of focus on water usage in the state of Arizona. And you've probably seen some recent articles about, certain parts of the state actually starting to run low on water. Of course, we've all seen Lake Mead, in the Colorado River. The drought has caused significant loss of water in that reservoir. And so to support our commitment to achieve a net positive water use, we funded 16 water restoration projects benefiting Arizona. And these projects restored more than 800 million gallons of water in 2021. And there's a few examples of those. On the Ocotillo wafer fabrication site, there's a brine reduction facility that we developed in partnership with the city of Chandler. We've been operating this since 1995. And then we have a newer facility, which is a 12-acre water recycling and treatment facility, which can treat up to 9 million gallons of water per day. So a lot of focus on, reusing, recycling, and providing water to the community, creating this net positive water usage. We've also done a lot of work in workforce development and finding more pathways for people to find jobs in the semiconductor industry. And specifically in Arizona, we've worked closely with schools all the way, K through 12, into community colleges and into the universities. So we have a K-12 STEAM education pipeline where there's a number of programs where we work with these, elementary through high school schools and nonprofits to realize the power of, the ability to help develop and prepare these students for potentially working in a technical position in the company. We've also worked with the community colleges and trade schools. We have a program with Maricopa Community College called Quick Start, where we're basically created classes to help teach and ready people to take on technician roles within our wafer fab. So it could be repairing or doing maintenance on equipment, to running the equipment to build the wafer. And then we've also got several collaborations with the university. We support Arizona-based research. We support scholarships and internships. We've also worked with the three primary universities in the state, ASU, U of A, and NAU, to work on curriculums to meet the needs of the students and align them to the industry. Some other examples of investing in Arizona. So we've got 1,000+ Arizona teachers, schools, and nonprofits that are supported by Intel and the Intel Foundation. We had 554,000 hours volunteered at Arizona schools and nonprofits since 2017. And we've had 27 million contributed by Intel and the Intel Foundation to these Arizona schools and nonprofits since 2017. And I'll finish just by sharing a quote from Robert Noyce, the co-founder at Intel. This is one of my favorites. Don't be encumbered by history. Go off and do something wonderful. And Sammy, I think you were going to share some slides next.
Yes, I think you need to end and I will share mine.
Okay.
Yeah, thank you very much, Chris, for helping us set the stage for today. And Sammy, we'll turn it over to you.
Thank you, David. All right, so I'm just going to talk a little bit about, some of the different things that we're doing here at the University of Arizona that's related to semiconductor and microelectronics processing. So as Chris very nicely said, semiconductors are critical to the state of Arizona. Intel's invested a tremendous amount into the state economy. But, coming from a materials science and engineering background, I like to say that, materials really enable technology, right? Starting from the Stone Age to the Bronze Age to the Iron Age, people now refer, to the current age as being the Silicon Age, because silicon has the creation of things like microchips that have enabled us to go into this, realm of information communication technology, right? So the semiconductor market is huge. If you look at projections for the next 7-8 years, I think it's annual 12% growth in the microelectronics industry. So we're going from 500 billion plus a year to over $1 trillion. So there's substantial demand for microelectronics to enable all the new interconnected devices and big data centers, et cetera. So Arizona is quickly becoming referred to as being the Silicon Desert. We know Silicon Valley out in California, that's where I grew up. Here in Arizona, now we've become the Silicon Desert. So in addition to Intel investing significant amount of money into creating new fab facilities, Sammy is also creating 2 new fabs north of Phoenix. So this represents, the largest foreign direct investment in the state of Arizona throughout its history. So currently there's, over 100,000 jobs tied to the Arizona semiconductor industry. With these 4 new fabs coming online, this is going to create thousands of additional jobs. So, we're here at the University of Arizona. We're looking forward to, developing students that will graduate and be placed into a lot of these positions. So, if you look at, the National Semiconductor Economic Roadmap, they clearly state, what are the things that the state should be investing in to help grow the semiconductor manufacturing industry. We need the infrastructure. We need, the Intels, the TSMCs to create these fabs. But to support those fabs, we need supply chain, right? So we have a significant supply chain here in the state of Arizona, as well as out, in our neighboring state of California. What is currently lacking, however, is the workforce. The University of Arizona will contribute significantly to developing the workforce that will feed into the growth of the semiconductor manufacturing industry. Being a university, we're also keen on innovation and entrepreneurship. We want our students to be creative thinkers, critical thinkers that will develop innovative solutions to help continue to push the forefront of technology in this area. So just, quickly going over the manufacturing of semiconductor devices, right? These devices are made out of silicon. Where does silicon come from? Silicon comes from basically sand, silica sand, right? We take the silicon, refine it into silicon, which we then grow very carefully into single crystals, large single crystals. We cut the single crystals up into wafers, and then we use very, very expensive UV systems to do photolithography to write very, very fine scale features. And I think now you can write features as small as 3 nanometers in size, right? So the manufacturing of a semiconductor device is very similar to that of 3D printing or additive manufacturing, where we're creating things layer by layer. But manufacturing a semiconductor device is actually more complex, because not only are you adding things, you're removing things, changing the chemistry of the different layers, you're growing insulators, you're adding metal layers, you're chemically, mechanically polishing off layers, you're adding interconnects. And then at the end of the day, you wind up with lots and lots of little devices on a wafer that you can then cut up and package into a device. So there are various different aspects and skills and materials that are needed to really create a semiconductor or microelectronic device. So here are a couple of plots that I kind of pulled out showing the state of the domestic semiconductor material supply chain. So on the plot on the left, this is basically showing the United States contribution to the semiconductor manufacturing industry. Although I guess the lightish blue is the U.S. share. So the U.S. has a huge share in terms of owning the intellectual property, the design aspects, some of the equipment manufacture associated with microelectronic devices. But in terms of the actual production of semiconductor devices, production of the materials that are used, et cetera, we own very, very, very little of that occurs domestically. So only about 8% of all the microelectronic devices are produced here in the US. If you take a closer look at the actual materials that are being used, the distribution of the materials that are being used, we produce very, very little in terms of the raw materials, the raw silicon, the critical minerals, all of that is produced outside of the US. And there's a need to kind of build up a domestic supply chain that kind of feeds into that. So what's glaring is that, in the wafer industry, just producing the wafers, little to no wafers are produced here in the US. So this is, considering what we've known, the lessons we've gone through with the pandemic and, all the volatile issues that are occurring internationally, this puts us in a very precarious situation, right? We cannot be totally reliant on external sources to be able to successfully continue manufacturing these critical devices. So the semiconductor manufacturing industry is going to continue to grow over the next decade. If you look at the various reports, there's hundreds of thousands of new jobs that are going to be needed in the US, not only on the manufacturing side, but also on the design side to support the growth. And this is not just growth this is not just need for mechanical engineers or material scientists or electrical engineers. It's a very, very interdisciplinary skill set that the semiconductor manufacturing industry needs for growth. Here at the University of Arizona, I think we're in an excellent position to really capitalize on the investments and the growth in this area. We have a micro nano fab here at the University of Arizona that is actually used to train students to make microelectronic devices. This is a key skill or attribute that we have that not many other universities have. We have an extremely rich legacy of, contributing significantly not only to research and development, but also development of workforce for the semiconductor microelectronics industry. We have literally thousands of alumni from the University of Arizona working in the various microelectronics companies around the United States. Here in the MSE department, we offer a 2-core sequence. One is a lecture related to microelectronics processing, and another is a laboratory, hands-on laboratory, where students actually get to use our micro nano fab and manufacture microelectronics. For many years, the College of Engineering housed a National Science Foundation Engineering Research Center for environmentally benign semiconductor manufacturing. We graduated hundreds of graduate students. Professor Farhang Shadman, Professor Sweeney were instrumental in really building up that capability here at the University of Arizona. So we're continuing to, considering the passage of the CHIPS Act and all this activity, we're actively working on building a lot of workforce development programs to train, our 4-year STEM students, but also looking at exploring the need to create these, stackable certificates that can be used for upskilling of, industry personnel or vocational students, because that is also what is needed to kind of support all this manufacturing activity. We have a tremendous amount of ongoing activity in quantum materials, quantum devices. We can kind of integrate a lot of those activities under this one umbrella, and maybe even, think about creating some distinctive curriculum and certificates based on this this field. Over the past year, we've been working very closely with a number of our alumni. We've been working towards, establishing formal internship co-op employment pathways for a lot of our students here at the University of Arizona. And, last year I looked at, the employment diversity statistics in the microelectronics manufacturing community. I think 85% of the employees working in the semiconductor industry were male. It's not a very diverse workforce. We can, being a minority serving institution here at the University of Arizona, I think we can really contribute to balancing out that workforce. We have a number of programs here that are specifically designed to lift up, underrepresented minority students. The Engage program, the VIP program, that'll allow these underrepresented students to really develop pathways by which they can, use to gain jobs in the semiconductor manufacturing industry and really elevate their socioeconomic standing in the community. So we're doing a lot. And as I mentioned earlier, semiconductor and microelectronics research is very, very much interdisciplinary. There are many aspects of engineering that need to be assimilated together to really push the edge of innovation in this field. It's not just only, material science and engineering, it's also electrical and computer engineering, systems, industrial engineering. We need to, copper and gold are critical materials for these microelectronic devices, right? We have to mine those resources. Mechanical engineering, thermal mitigation of these high-end devices is a huge challenge in the industry. So we also have to work on that. And then, a lot of the issues around water, sustainability, chemical, environmental engineering are also really important. So with that, that ends my brief overview of what my perspective is on semiconductor materials and microelectronics manufacturing here at the University of Arizona.
Excellent. Thank you, Sammy. If you want to unshare your screen,
Sure.
we'll dive into this. So first, I want to thank you both for really helping to set the stage for this discussion. The audience members have pre-submitted questions, of which I've pulled some. Some of them you've already got into in partial your answers. You both really set a comprehensive background, so might be a little redundancy as I try to navigate what's been asked and what you've addressed. I'll also, in real time, we're getting some really good questions. So I think this is the exciting time. So Sammy, I'm going to start with you. Again, you've hinted at it, but what ties do we have now with Intel and TSMC and perhaps others in the state and region regarding collaborating on education and research? And how might we get better at that as we look forward to engage with the state's economy?
Sure, that's a great question, David. So we get better by working with people like Chris, right? Having people like Chris serve on our Dean's and Industrial Advisory Board. So in the MSE department, we also have Dr. Ravi Mahajan from Intel, who also serves on our MSE External Advisory Board. He's been instrumental in terms of helping to champion getting Intel input into our curriculum. Dr. Ravi Mahajan has served on our faculty search committees. He's provided a lot of input into what we should be doing, how we should be leveraging our existing capabilities to pursue larger research efforts. So we get better by working with the folks from Intel. So we also have this past year we hired Professor Zafar Mutlu, who's been incredibly successful despite being here only 6 or 7 months. He's already gotten 2 workforce development grants related to semiconductor manufacturing workforce development. So he has a lot of very strong connections with the folks working at both Intel, TSMC, and he has a lot of really good ideas on how we can create modular laboratories and disseminate knowledge to not only 4-year STEM students, but also vocational students. So there's a lot of activity that, we're really trying to leverage and put ourselves in a good position to really pursue.
That's great. I mentioned in my introduction, the Arizona Commerce Authority, they have $100 million and to really foster innovation and education and research around the semiconductor and to really work with the universities to build infrastructure so that we can support the industry of Arizona and also be prepared to better leverage the CHIPS Act. So it's pretty exciting. Chris, do you want to elaborate from where you sit on the Intel side about how you look to the universities of Arizona? As I mentioned, you're on our advisory board at the college level, which is really helpful. So we appreciate that insight and share any additional thoughts you might have on this topic.
Yeah, I'd be happy to. I talked a little bit about it in the intro slides. We do have partnerships with each of the 3 universities here in Arizona. And I think if you look at the last couple of years, we've really increased the number of employees that are directly engaged with those universities. So Sammy mentioned Dr. Ravi Mahajan is one example. Dr. Tom Rucker is also very much involved with the universities, not only in Arizona, but across the state. One of my direct employees, Matul Modi, has been working directly with ASU on curriculum development and helping develop that workforce plan with that university. So you're seeing an increased number of employees and level of engagement directly from Intel employees, and hopefully we'll have an even bigger impact on collaborating with those universities and building up this workforce pipeline. Some other specific examples, we've done quite a bit of sponsorship of research programs at the universities as well. And this is another area that we've increased our focus. So we provided collaboration and guidance to the universities on what equipment, what type of research focus they should have in semiconductor, either wafer manufacturing or in advanced packaging. We've also done a lot of internships. So we've hired quite a few students as interns from both U of A and ASU in the last few years. And then we see many of those interns turn into full-time jobs as well. So in my organization, I know we've hired 30 students from U of A and ASU in the last 2 years. So, pretty large population of incoming students from the Arizona universities. We've also got a really good partnership with the community colleges too. So a key area to support manufacturing in the state of Arizona is to have these technicians that can repair, work on equipment, run equipment, and really run these advanced manufacturing processes. And there was definitely a shortage of available workforce in that space. So we developed very specific programs to help train, either through a 2-year degree or even through a quick start program to get them ready to be, hired on and come into either Intel or TSMC and support those manufacturing jobs.
That's exciting. On that latter note, as I mentioned, we're working right now with ACA on a proposal to have some of that funding that they have invested in us. And we are partnering with Pima Community College just for those types of 2-year degrees and other skills that I know you so valuably need besides full, bachelor's and higher level engineers. So it's exciting to hear, you push that broad approach. And, as the land grant university of this state, we very much take our mission of education and our partners with the community college system very seriously, because you need the whole spectrum, right? And well, you won't meet your workforce needs, and workforce is really an exciting thing right now, and the opportunities it provides for the technical disciplines like engineering. Chris, I'm going to stick with you for a minute. And what I really always value and enjoy about our alums and friends is that they love to get technical. So I'm going to pull a few technical questions, one that was pre-submitted, one that popped up online just a few minutes ago. So with the migration from FinFET, which I had to Google, fin-shaped field effect transistors, to what they call gate-all-around technologies, what are some of the biggest challenges that a device maker like Intel faces?
Yeah, this is a really good question. It's a very important transition, actually. If you look at the scalability of FinFETs, there really wasn't a roadmap beyond 3 nanometer for FinFET. And so the gate-all-around transistor was invented a number of years ago, but was never really brought into high-volume manufacturing. And we see that as the key way of scaling these transistor dimensions below the 3 nanometer node. And gate-all-around transistor, also called ribbon FET, is another name for it. But it's a technology that helps to reduce leakage and increase the transistor drive current. And this enables the transistors to switch faster, but also run at lower power, which is very, very important, for continuing this increase in compute power. If you look at the manufacturing required, we're talking about very, very small, fine dimensions. So these critical features are measured in the angstrom scale.
Wow.
So you're not even talking about nanometers anymore. You're talking about rows of atoms, essentially. So the key issues in manufacturing these devices, number one is the number of defects that can be produced during the manufacturing process. You've got a lot more area within the transistor now for defects to form. We need very advanced process controls. And one of the critical issues is that we don't have very effective non-destructive metrologies to both be able to measure these critical dimensions, but also to identify defects that are produced during the manufacturing process. So a lot of the metrologies today are destructive in nature. So it doesn't give you the ability to get real-time feedback on your manufacturing process and correct any defects, before they affect multiple wafers or multiple wafer lots. So that's definitely a key challenge with this gate-all-around transistor.
And I'll pull one in real time about your very advanced packaging program, your Phobos technology. I hope I pronounced that right. Is that intended primarily to improve electrical, thermomechanical, or thermal management performance, or perhaps all of them?
Yeah, the Phobos technology, the key advantage of it is it gives you the ability to connect these multiple chiplets together at very, very fine pitch. So if you look at a multi-chip package where we attach the chiplets directly to an organic substrate, there's several limitations. One of them is because of the CT mismatch between the die and the organic package. During the formation of those interconnects, you have a mismatch in the expansion of those materials, and it limits your ability to scale the pitch down. So today we're shipping products with a 55 micron pitch between individual solder joints connecting the die and the package together. We see a roadmap to scale that down to 45 micron, but going below that is very challenging.
Wow.
So what we do with the Phobos technology is we actually attach these individual chiplets to a base silicon wafer. So that eliminates one of the key challenges being the CTE mismatch between these two things. And if you look at a base silicon wafer, not only does it have a matched CTE, but it tends to be very flat as well. And you can use very advanced fab type processes to planarize and form, using plating to form those interconnect solder joints. So it gives you the ability to scale the pitch. We've already produced packages with a 36 micron pitch between individual solder joints using Phobos, and we see a roadmap to scale that below 20 microns.
Wow.
So you can get a lot more interconnects connecting those individual chiplets together. And when you do that, you can change the way you communicate between the chiplets. You can go to more of a wider IO and at a lower frequency and reduce the power that is required to talk between those individual chiplets.
Wow. When you talk about tens of microns, it's like aligning human hairs, right? I mean,
right.
That's wild.
Yeah, and then the next technology we're working on is the Phobos Direct, and we see that as the pathway to go below 10 micron pitch.
Very nice. Thank you. Sammy, I know you've been with us about a year and a half. You hinted in your opening presentation some previous relationships with Intel. Sweeney has put online that we used to have a program where we would help technician level employees at Intel move towards a bachelor's degree. So if you want to comment on some of the previous efforts and maybe some current efforts and looking forward, please do that. And then if you want to kind of go a little further ahead to kind of look at what AI role can play. So I'm pulling the three questions together because I know you can handle them all. So Sam.
So Sweeney's, was a longtime faculty member here, and he was instrumental in helping put together, I guess, an Intel Online Bachelor's of Science degree in Materials Science and Engineering with Intel. So this was a program that was put together with Intel where we would basically offer a full MSc bachelor's degree to like technician level workers so that they could get credentialed and move up. So that was, I think, probably 15 years ago. I believe that's when that program started. In terms of what we're doing now, I mean, we're doing, I think, quite a bit in terms of materials development. We're Professor Mutlu here in MSC's looking at creating graphene ribbons to kind of support some of these advanced technologies. In terms of how AI and machine learning are impacting the semiconductor manufacturing industry, I think a lot of the microelectronics industry have really adopted a lot of these big data type of technologies, right? They're monitoring power consumption, water quality, just about everything. They have sensors, it's an automated line. They have sensors embedded in everything. They're collecting all this data and correlating it back to their yields of their devices, right? So I think, they've used AI, they are actively using AI machine learning to create digital twins of their entire manufacturing process. And I think, more and more manufacturing industries are adopting these types of technologies going forward. And I think that's the future of manufacturing, to tell you the truth. We talk about, the fourth industrial revolution, or that's what it is, I believe.
Absolutely. Very good. Very good. Chris, one thing that is often discussed in the context of semiconductor industry expansion in the greater Phoenix metro area is water usage. You did have a nice slide about that. I'll ask you if you have some additional thoughts on water reuse mitigation, but you can take it a little broader about general sustainability, carbon mitigation in Intel's investments and expansion. I know it's important to your company and it's important to the people of Arizona. Do you want to talk some bigger pictures of how Intel views sustainability?
Yeah, I'd be happy to. I think this RISE 2030 program that I mentioned has been a really important vector for the company. We've used that to set annual targets for, basically reducing our carbon footprint, reducing our electricity and utility consumption at the sites, as well as water usage. And so we've set very aggressive goals every year. And we also have an annual process where employees submit their project for consideration for award. So basically they summarize the environmental impact that their project has had, and then they're put up for awards. So it's been a really neat program, really to help inspire and recognize the work that is going on by various groups across the company. In the last couple of years in my organization, we have won both bronze and silver awards in this category for environmental sustainability. And I have an employee now full-time working on sustainability and as well as cost reduction. A lot of times those types of projects are tied together. And there's a lot of excitement in my organization on, driving projects that reduce our environmental impact, into climate change. I talked quite a bit about the Ocotillo wafer fabrication site. So wafer fabrication uses a lot of water. So that's why there is so much focus on reducing, recycling, and trying to become net positive in water usage, particularly in Arizona, but also on our other wafer fabrication sites around the world. The work area that I work in is in package assembly. And we also have a few processes that consume a lot of water too. Particularly, we have an operation called deflux. And this operation uses high temperature deionized water that we spray at very high pressures in order to remove flux and paste residues from the package. And we do this multiple times through the process flow. And those tools consume a lot of electricity. They consume a lot of water as well. So we've had a lot of focus, even going back 10 years ago, in reducing the environmental impact of this process. So we've made the process more efficient. So we basically sped it up by making configuration changes to the tool so we can basically get more units out per hour out of a single tool. So reducing the number of tools that we have in the factory. We have also reduced the temperatures that we process the water material at. And then recently we've enabled what's called a sleep state. So the tool is allowed to go into an idle mode if there aren't any devices inside of it. So these are some other examples, even within package assembly, where we're reducing our water usage too.
That's outstanding. I often talk with our students about the importance of working at scale, right? The semiconductor industry is one of scale, $60 billion investment in between you and TSMC. So when one can affect change at the scale that you work, you really have some significant impact to the overall environment. So it's great to hear that Intel is pushing the limits on that. Sammy, let's come back to workforce because it's so important and the role of universities such as ours. You want to talk a little bit more about manufacturing? You can kind of go manufacturing writ large. You can go beyond semiconductors on how we seek to work with industry to promote, our education mission, our land grant mission, and workforce development to the state and region.
Sure. University of Arizona is the flagship university for the state of Arizona, right? So we have a mission to, not only serve our students, train them, educate them, but we also have a mission to kind of serve our community as well. So, manufacturing jobs in Arizona are growing, depending on, when, or, depending on what publication you read. Governor Ducey's mentioned, 500,000 new jobs being created in the state of Arizona over the next 10 years, right? So I think advanced manufacturing, there's a lot of potential, and a lot of these advanced manufacturing jobs, they're not the minimum wage jobs that kind of keep people at the lower rung of the socioeconomic ladder. These advanced manufacturing jobs can really kind of elevate, individuals, particularly those from underrepresented communities, into a different socioeconomic status. And we're committed to helping those, not only our 4-year STEM students, but we're committed to helping everybody kind of grow and elevate their socioeconomic status. By how we're doing that, we're working very closely with different manufacturers. We're engaging them. We're trying to develop internship opportunities, co-op opportunities, so that our students, as soon as they enter the program, they can see pathways by which they can choose, right? So like a material science and engineering student, they can come in. If they're interested in microelectronics, they can take courses that put them along a pathway that will prepare them for a career at Intel or TSMC. If they're more akin to, let's say, the aerospace industry, they want to make, parts for jet engines, they can take classes in additive manufacturing, in metals and ceramics that will better prepare them to pursue a career, to support the hypersonics industry here in the state of Arizona, right? So we're trying to create flexibility in our curriculum that will provide them with the expertise that they will need to be successful in whatever field that they want to choose.
Outstanding. Chris, I'm going to go back to you and go back to, again, some comments from my introductory remarks about the CHIPS Act. The CHIPS Act it's really a partnership. It allows companies like Intel to make significant investments with your dollars, but then leverage additional federal dollars and resources and programs. So it's a coming together to get something more than either side can maybe do alone. Do you want to share any thoughts on the CHIPS Act and how Intel is leveraging that? And then I'm going to pull an additional kind of question into that from a good friend of the college, Scott Roberts, who asks, where are the gaps in world-class technology, and how is Intel positioning to close that and again, maybe use the CHIPS Act? So again, a lot in there, but some really exciting opportunities.
Yeah, so the CHIPS Act was a very important piece of legislation to support, investments in U.S. semiconductor manufacturing. Intel played a really big role in not only the creation of that CHIPS Act, but also getting it approved through Congress. And we were really excited, when it was formally approved and announced. So we've been using this CHIPS Act. We've been working with the federal government to get some proposals approved so we can accelerate our investments in U.S. manufacturing. Last year, we announced a $20 billion investment in Ohio, creating 2 additional wafer fabrication sites. And the site is very large. We can actually, I think we can install 6 additional wafer fab buildings on that same site. And we're hoping to get dollars from the CHIPS Act to help accelerate that investment and, helping to grow the footprint of U.S. semiconductor manufacturing. The other thing we're doing with regards to the CHIPS Act, there's dollars set aside for advanced packaging as well as design centers. So in my organization that I work in is ATTD, it's Assembly Test Technology Development. We have been working on proposals for both the design center as well as having, a US-based semiconductor packaging facility here to support the federal government. We've also worked on some proposals with universities, and we've provided some collaboration and feedback and advice to the universities on their own proposals, particularly in the area of workforce development.
That's exciting. Wow, it's great. Lots of opportunities. Again, Sammy, looking at you, I noted that the Arizona Commerce Authority has funding to help us with investment to shape infrastructure. Do you want to comment on what are the critical infrastructures that we might invest in to broaden our support of the semiconductor industry, including things like quantum technologies, photonic electronics integration? Really exciting. We're really a world's leader in quantum technologies, and that all kind of goes together to look at what the future is going to look like. Do you want to give some thoughts on where we need to go and how we might get there?
Totally. I can sure help ACA spend that $100 million. So, micro nanofabs are significant investments, and, they rely on key instrument. So we want modern facilities that when our students use these pieces of equipment, they are almost analogous to the ones that they would use if they were working at Intel and TSMC. We want them to have that type of knowledge, but we also want a fairly versatile line that can be used not only for workforce development, but also support the research efforts that we have here across campus, right? So, things like metrology systems, advanced metrology systems, e-beam lithography systems, plasma etchers, plasma cleaners. A lot of those tools, are common to both workforce training, research. In addition, there's the whole packaging, microelectronics packaging realm that's also common to both, semiconductors and quantum materials, right? So, we've been doing a lot of work on developing quantum materials, but at some point you need to move those materials into a device. We need to be able to fabricate devices that harness the unusual properties of these quantum materials and create something tangible out of it. So, packaging, heterogeneous integration, a lot of that modernization that is needed in our micro nano fab could very well benefit from these investments or potential investments by ACA.
Right, good. Chris, we'll kind of stay on the topic of quantum for a moment. One of our friends, alumni in the audience submitted the question, will Intel be making photonic integrated circuits for quantum applications in Arizona? And feel free to kind of share on any thoughts you have looking, again, I know Intel's always looking what's next, what about quantum enabled applications in semiconductor manufacturing?
Yeah, so a lot of the research that we're doing on quantum computing devices is done in our labs in California and Oregon. There's not a lot of activity in Arizona so far. We have done some work in Chandler, working specifically on packaging materials and interconnects. One of the key challenges with the quantum devices is that they run at extremely low temperatures. So that is a new and unique challenge for those devices. So we have supported that area of research, and we've actually built some devices out of our Chandler R&D facility. We haven't made any formal announcements or plans on manufacturing of those devices. They're really at lab scale today. But I think this is a really exciting emerging field in computing. There's a lot of challenges in creating what I would call a scalable and manufacturable architecture to support quantum computing. So I think there's going to be a lot of innovation in this space in the next 5 to 10 years.
I agree. It's really the leading edge of technology. So it's exciting. One person asked that there's modest production of sort of semiconductors in the Tucson area. How will we, University of Arizona Engineering, help to potentially scale that up? So I'll just answer first that we work very closely with the Arizona Commerce Authority, with the Arizona Technology Councils, particularly their Southern office. Carla is on our advisory board, the Tucson Metro Chamber. Michael is on our advisory board about business recruitment, including the semiconductor industry. So it's something that we are very committed to, is growing that Southern Arizona economy in these high-tech areas. Chris, I'll turn to you because you mentioned in your introductory slides about indirect jobs, I think 15,000, which is really exciting because people think of your fab, but there's a whole ecosystem around it. You want to talk a little bit about the importance of the larger sort of ecosystem supply chain that revolves around an investment like Intel and how that also drives jobs in the economy? And how important it is to you.
Yeah, certainly. I'm not aware of any Intel plans for direct investment in the Tucson area. I think the opportunity is more where you mentioned in the indirect opportunities around supply chain. And that could be in service, there could be, opportunities in doing offsite repair or recycling of our materials. There could also be opportunities in providing some of the direct materials that are used in our wafer fab and in our packaging environment too. We also, through the pandemic, we have moved to a hybrid workforce where we have employees working part-time from home and they're spending a little bit of time on site. So the other thing we have seen, we do have employees that are living in the Tucson area and working from home, 3 or 4 days a week, and then commuting into Chandler, either the Akati or the Chandler site, a few days per week for on-site activities.
Very good. So we're kind of coming up on the top of the hour, so I'll go back to technology again, because again, this is what our team out there always likes to ask. So knowing Moore's law, Moore's theory, which basically says that transistor density doubles every 2 years. What are we starting to hit the limits? You hinted at this, Chris, right? Kind of 2 to 3 nanometer features. I mean, you're getting down to angstrom, atomic lines. You want to talk a little bit about both of you about the limits of where we're going?
Yeah,
Yes.
I'll start. I guess I'll say, since I started working in the semiconductor industry 25 years ago, there's always been concerns about what's next. Can we continue to scale this, technically? What's beyond 45 nanometer? Do we see a path beyond 16 nanometer? So I think the concern has always been there. We've always found technical solutions to continue scaling. And as I mentioned earlier, this gate-all-around technology we see in the near term as the way to continue scaling beyond 3 nanometer. I think as we look further in the future, there's going to be more emphasis in probably 3D stacking of transistors within the device. And I think that's how we'll enable that, continued transistor density scaling.
Very interesting. Sammy, you want to weigh in a little bit?
I totally agree with Chris. I mean, he has firsthand knowledge of what Intel's planning on the future. I mean, they've been talking about Moore's law potentially not being valid for the past 20 years, right? But every year or every couple of years, they come up with technological solutions that can allow Moore's law to continue. So I think silicon is going to have a long life, especially with these 2 new fabs, or that Intel's building. These 2 new fabs that TSMC is building. Silicon's going to have a long life. Heterogeneous integration, stacking of chips, the chiplets, combining the chiplets, that's really going from a 2D architecture to a 3D architecture. All those are significant advances that are going to, I guess, continue to propagate Moore's law for silicon. So until the day comes where, they decide that they need a better material like graphene or, carbon nanotubes or even cubic boron arsenide, I guess, what was recently discovered, I think silicon's going to have a long life, at least for my lifetime. I think we'll still be using silicon.
That's good. That's exciting. We're kind of coming up to the end, so I'm going to stick with you, Sammy. And sort of the politics shaping global manufacturing, are you seeing, because this is your area, again, beyond just semiconductors, are you seeing more onshoring back to the U.S.? And is that providing us, where we sit in the university, some exciting R&D opportunities on the collaboration fronts? How do you see that shaping up?
Totally. I think, the global situation has changed, right? 20 years ago, it was all about offshoring, I think, globalization, right? China is the factory for the rest of the world. Right now we're bringing a lot of the critical manufacturing back into the U.S. And this is going to lead to lots and lots of opportunities, because a lot of the technological know-how that used to exist in the United States has really thinned out. So there is a real need, a real demand for basically reinvigorating and generating a new generation of engineers and scientists that has that technological know-how and can continue to push the forefront of innovation in advanced manufacturing. So, people say it's the end of globalization. I say, that's probably true for most things, but, we are strategically building a lot of in-house manufacturing capability back in the U.S. Not just, Arizona is really benefiting from a lot of the nationalization, but I think there are other areas that are also being pulled back to the U.S. as well.
And Chris,
but this creates a lot of opportunities.
Absolutely, Chris. You can give me 1 minute on that similar question in the context of semiconductor and global forces. Again, a complicated question, but this is your expertise, so you want to give us a closing thoughts on that?
Yeah, and I completely agree with what Sammy said. I think the COVID pandemic kind of started the realization of how fragile our supply chain is. And there is a heavy density of semiconductor manufacturing and raw materials in Asia today. If you look at wafer fabrication, a lot of the wafer fabrication around the world is done in either Taiwan or South Korea. Intel is really one of the few companies that has significant wafer fab capacity outside of Asia. And our footprint is primarily in the US and Europe. And so, there's I think a need not only by companies, but also by the US government in the EU to grow that because of potential national security concerns. So you can see there's a heavy interest from them in, growing that semiconductor manufacturing footprint outside of Asia. And so I think we're going to continue to see that trend. We'll see more manufacturing move into those areas. I think we'll also see more of the raw materials trying to come out of the US and EU just to kind of rebalance the supply chain around the world. And I think you're right. I think the US infrastructure will be one of the key beneficiaries of this remigration back into our space.
That's great. The time has flown by. It's been a fantastic conversation. I've enjoyed every minute of it. I always say these conversations are great, but this has been a really exciting and informative discussion of a topic that is really at the top of conversation in this country right now. So thank you both. I want to thank our audience for sticking with us and providing some great questions in advance and in real time. I hope to see everybody next month on March 8th at noon, when we will talk a little bit about related topics, critical minerals, materials, with our mining department chair, Craig Luxbacher, and our alumnus, Greg Boyce. So I'll see you then again today. Chris, thank you so much. Sammy, thank you so much as always. I wish everybody a great day. Bye.
Thank you. Bye.